Well, thanks for the introduction. Today I'm going to present a result that concerns certain situations where we deploy crypto hardware or systems in the field, and we do not know how often this hardware is used. So use can mean different things here. So use can mean, for example, it could mean generations of signatures, but it could also mean generations of ciphertext or just applications of the key generation function. So how often do we generate keys for a certain crypto system? So now there are in general two possible ways how these systems might turn out. So either security and security of the system is based on the number of applications of those systems, or it's not. So for practice, usually the latter case is much more preferable because we can have security guarantees without worrying about future uses and attack behavior. Attackers might use the system as well and kind of scale the number of applications of the system. So what I'm now going to do is I'm going to slowly lead to a very general result, and what is relevant for long-lived systems is rather a corollary of that. So, but I'm going to start off with digital signatures and provable security. So bear with me; it's going to take some time, but I'm going to make it entertaining, hopefully. Okay, so let's start. Okay. So I'm going to talk about provable security and tightness and a certain important existing result on tightness. Okay, this is resulted by Courant, and this has been, and it's kind of about 10 years old, and it's kind of a seminal work. And so what we did is we developed the result further in some direction that makes it applicable to other important scenarios as well. So and then I'm going to briefly give a interpretation for this result with regard to long-lived systems. Okay, so what is provable security and how do people usually produce secure systems? First of all, they define a security model. What is meant by security? In particular, this usually means define an attacker, a successful attack on the system. In this case over here, we consider an attacker that breaks a signature scheme. Okay? The attacker gets a public key and may ask and request several messages of its choice, q times, as often as it wants, to get back some signatures. So the attacker just asks for some messages and get back signatures. And the task of the attacker is to produce a forgery, meaning that the attacker should output a message and a new signature that have not been received previously, which are also valid signatures. This is a very clean model, okay? Very simple model. Okay, so, and in provable security, what would we like to have in those situations is that given such an attacker, assume there's a successful attacker which produces a forgery in this sense, then we can have an algorithm which is called the reduction that takes this attacker, will use the adversary in some way and break some hard problem. Okay, this is the spirit of provable security. This means that if this problem is really hard, okay, such an attacker cannot exist. That's the basic idea. Okay, because whenever there's such an adversary, and we have the reduction, then we can also break the supposedly hard problem. But as we assume the problem to be hard, like factoring, for example, or the discrete log, such an attacker cannot exist. Okay. So now we might have a look at some metrics on both the adversary and the reduction. So the attacker the efficiency of the attacker is usually quantified by its running time, TA, and its success probability, success A. Okay? And the reduction is quantified similarly by a running time and some success probability. And there's some notion which is usually called tightness, which says that the reduction that given such a successful adversary which breaks this problem is called tight if the running time of the reduction is close to that of the adversary and the success probability is close to that of the adversary. So both use approximately the same resources. Okay? It also means that breaking the signature scheme takes almost the same time and resources as breaking the problem, this hard problem. Okay? Okay, so why do we care about tightness at all? So tightness is interesting from a theoretical standpoint. So we are kind of interested on how tightness scales with system and if there are some lower bounds, but it has also a very strong practical motivation. So namely, if we select parameters of a crypto system in a theoretically sound way, such using the results that we obtain from this reduction, if we use it in the theoretical sound ways and derive parameters in the theoretical sound way, then we have a certain situation. Tight reductions give smaller parameters than non-tight reductions. Then reductions where the reduction is less efficient than the adversary, significantly less efficient. So this kind of theoretical looking thing really translates to practical parameter sizes. Okay. So as for tight schemes and for tight and research on tight reductions, we do have a lot of stuff already. There are tight schemes for identity-based encryption, public key encryption, key exchange, digital signatures, and pseudorandom functions. But they are all kind of different, and it's really hard among them to spot some pattern. And what we were interested in is if there was if there are some properties that among these schemes that all tight schemes must have to allow for tight reduction, which again results in very efficient parameters. Okay? Okay, so once again, the game for signatures. So it's quite good if we keep it in mind. We will later on come back to that. So this is a scheme for signatures. Again, the adversary gets the public key, may ask for some messages, get back signatures, and outputs a forgery. Produces unique signatures. This means for every message, there's only one signature for every message. Then we can show that any reduction cannot be tight. Any reduction cannot be tight. This means that there is always a loss of Q. A loss of Q over here, the number of adversarial keys to the signature oracle. Okay? Q signatures, and this means that the efficiency of the attack that solves some underlying problem is just weaker. It's weaker by a factor of Q. Okay, and I'm going to show what this means more concretely right now. So it more concretely shows that given a reduction, given this reduction over here, which uses a successful adversary to break some problem, if this is the case and we have unique signatures, that's the point, right? If the signatures over here, there's only one signature for every message, then we can exploit that reduction. Then we can take this reduction, which supposedly exists, and break the problem almost in an instant. If such a reduction exists on adversaries against unique signatures, then we can almost immediately break the problem at hand. But this problem at hand is supposedly hard, right? So something is wrong there. And it turns out that the following theorem holds, okay? So basically, essentially, if the reduction over here exists, then we can build something, something which is called a meter reduction that uses this reduction and just simulates an adversary, just stages an adversary that the reduction would like to use. And this meter reduction has some success probability in solving this supposedly hard problem, which is related in almost in this way over here. So it means, so to interpret it, we want that this problem is hard, so this value over here should be very, very small, negligible. So, and over here we have a 1 over q. So to make this difference negligibly small, this means that the success probability of the reduction should be close to 1 over q, not more. Okay? This means that the success probability of the reduction cannot be more than 1 over q. Otherwise, we could, with some probability, with good probability, solve this problem. Okay? But this is not all in the analysis of Coulomb. There's something more. There's an annoying term, okay, which also shows up over here. And this term says like, okay, this is not all. There's also another factor, and this factor depends on the number of queries, but also on the message space. And usually, the message space over here is exponentially large, and Q is polynomially large. So this means that this term usually is negligible, and we have almost a 1 over here. Okay? As long as the message space is exponentially large, we are fine. Okay? Okay, and this result is quite general for signature schemes. It holds for unique signature schemes, and it holds as long as the reduction that uses the successful attacker treats the attacker as a black box. But I would say the analysis is quite complex. So once again, it is useful for analysis of typical signature schemes where we have a exponentially large message space, but it's not useful if Q is almost equal to the message space. We would see that later on. Okay. Okay, so in the definition of security for signature schemes, we have only considered a single public key. Okay, just a single one. But I mean, in the internet, in reality, there are a lot of public keys. There are a lot of users. Okay, and well, the attacker may also kind of intercept data of users and also try to hack some users and get their secret keys. So in reality kind of forces to use a much stronger model, a much more realistic model. Okay, and such a model is this one. Okay, the attacker gets several public keys, public key 1 to n, and of course, so the attacker can also ask for some signatures on some messages of its choice, but this time it also specifies the public key the signatures should be produced with. Okay? But then the attacker can also ask for secret keys of other users. Okay, we have the internet, and there are some other users who did produce their secret keys with some algorithm independently of us, seemingly. And the adversary may ask those users for their secret keys. Right? And ideally, this shouldn't influence our security guarantees at all. Okay. So what we would like to have is, in an ideal world, we would like to have that the system, the choice of system parameters, is independent of the number of signature queries, Q, the number of signatures the adversary asks for, and the number of public keys. This is what we would ideally have, because then we could deploy the system and don't care about how long it's going to be about how long it's going to be used and by whom. Okay, and now there's a folklore theorem. You could say this is kind of a simple reduction that shows that, well, it kind of is okay to only concern oneself with a single user setting, because if the single user setting holds, then we can deal with the multi-user setting as well. So there's some transformation of this security notion into that, right? But this security notion loses a factor of 1 over n, the number of public keys. Okay, this is a standard transformation. Okay. Okay. So now again, we would like to use the result of Courant to show that in some cases this loss is, for example, we would like to analyze schemes and systems and try to use Courant's result on that, showing that sometimes a loss is unavoidable, like before, on unique signatures. But annoyingly, this time the number of public keys is only polynomially large. Okay, this means that, well, over here we run into problems. Okay? And we get a trivial bound. So this does not, because of this odd term, the message space over here, or the number of public keys over here, we run into problems and we get some bounds that do not give us anything. They're too bad. Okay? So, and what we can do is we could try to find some other solutions to come around this problem. So, and what we did is we found another way to derive these impossibility results. And it's surprisingly much more simple than the Courant analysis. So I'm going to show it to you right now, some intuition on that. And it's also at the same time much more general. So it's very versatile and it gives very strong results on important applications, actually. So I'm going to tell you about them as well. Okay, so first of all, we define a very weak game, very weak security. The adversary obtains public keys, chooses one at random, and obtains the secret key for all other public keys. Choosing one at random, getting all other secret keys, okay? And then the adversary needs to output this very secret key. Get n, get the secret keys for n minus 1, and output the last one. And we have totally ignored now generation of signatures. So what now is kind of obvious is that if we cannot have a tight security reduction for this attacker, for this guy over here, then there will not be a tight security reduction for any stronger attacker. And this is really stronger because, well, any attacker that obtains the secret key can also forge a signature. This is very weak. Okay. And on the other hand, right, this makes sense for any public key scheme. So there are encryption schemes, there are broadcast encryption schemes, the digital signature schemes, key exchange schemes. Whenever there's a public key, this scheme is kind of valid and realistic. Okay. So we would like to have a result without this annoying term over here. So how does it work? So we imagine an attacker that gets public keys, chooses one, gets the secret keys for all others, and outputs the secret key J, okay? So there are just two possibilities. Either the reduction that uses the attacker to solve some hard problem can answer the attacker for only one choice of J. There's only one choice such that the reduction works, or there's more than one choice. Just two cases. Okay? Now, if there's only one choice, this means, and this one is chosen at random, this means that the reduction can only have a success probability of 1 over n. there's only one choice, and this choice is chosen as random. It's independent of the reduction. So 1 over n, kind of trivial. Now assume there are two choices. Assume the reduction would work for this attacker for two different j's. Okay, then we can conclude that the problem, the original problem, is not hard. But of course, we just use supposedly hard problems, and well, this kind of excludes this case. Okay.
In the previous slide, the adversary has to choose at random the index, right?
He does that there.
But doesn't this restrict the class of adversary?
We just show for one adversary it's not possible to have a tight reduction. So if that's true, then it's true in general. Right, yeah. Okay, so here it is. We now assume that the reduction works for two different j's. So what do? In the first run, the attacker is given all the public keys. Now, so we assume there is some algorithm that exploits the reduction, the meter reduction, okay? And it stages an adversary, okay? Now this meter reduction is given n public keys. And the meter reduction behaves perfectly like the adversary chooses a j and get back the secret keys for all the other values. But it does so for all j's. It reiterates, okay? It starts off with j equal to 1 and then gets back all secret keys if the reduction is successful. Then it starts j equal to 2, j equal to 3, and j equal to n. And if there are two of them, and those two are distinct, then by just asking for all this n minus 1 secret keys, the meter reduction will receive all secret keys. Okay? For two different things, for two different j's, it will get n minus 1. Among all those, there will be all secret keys. Okay? So now, since reduction is an algorithm, and it outputs the public keys, we send over j equal to 1, get back the secret keys, and just rewind it to some previous state. Rewind it, okay? And then we can do that for all the other j's. And in this way, we can also get all the secret keys in case we have two j's for which the reduction works. Okay? Okay, so, and when we are through, and we know all the secret keys, we start off again for random j, and then we get all the secret keys, and we answer with the missing secret key that we've just obtained by rewinding the reduction. Okay, and this is also perfect. There's no difference in the behavior of an attacker that chooses this j at random. Right? We start off again fresh. There's some state, and we start off again. Okay, so when does this result work? In kind of similar to the result of Coron, it works if for each public key there's a unique secret key. But this virtually holds for all public key schemes around there, right? So factoring two factors, that's unique, okay, for the composite. And for discrete log, it's the same. So we have a cyclic group of prime order, and then there's a unique discrete log. So for all those schemes, we lose a loss in the number of public keys issued. Okay? In this strong model where we have corruptions and where the attacker may obtain several public keys. So actually, this is just one application of the result. The result is actually more general. It works for the multi-user security with corruption. That's what we've just seen. It works for signatures more concretely, and it works also for other things. For example, it works for non-interactive key exchange, where this result gives a bound of n square. So this means that we lose n square. Okay? So actually, so you could generalize this in that way. You have some statement and some witness for that, and as long as the witness is unique, and some other generalization would also consider re-randomizable witnesses. That also works. Then you could have a similar result. So it's only up to you to use this result and see in some security game that it's applicable. Okay? For example, public key crypto, then we have public keys and secret keys. But we could also have the signatures where we have M and NS. Okay, to sum up, so this is a stronger result on impossibility results for tight proofs. It has much more applications than the result by Courant, and it gives some way to easily check if a tight reduction is possible at all, right? So you do not need to try to improve reductions and get the parameter sizes lower and have more efficiency for a scheme. So if you can kind of see the pattern and apply this result, then it's optimal. Okay? So I guess that's it. Thank you very much.